So good morning, good afternoon, and good evening to you all, depending on your geographical location. On your geographical location. So today we are going to organize the one-day international seminar on mathematics and its applications, organized by the Department of Mathematics, Presidency University, Kolkata. So we are fortunate that today we will have two very excellent speakers. First one will be delivered by Dr. Shobbhusachi Dotto. It's my great pleasure to introduce Dr. Dotto. Dr. Shobbhusachi Dotto is currently a postdoctoral associate at University of Calgary, Canada, and he is working with one of the leading cryptographers of the world, Professor Safavi Naini. Prior to this, he was a postdoctoral fellow at Kyushu University, as well as Indian Statistical Institute, Kolkata. He completed his bachelor's from Ramakrishna Mission College, Narendrapur, and master's from Ramakrishna Mission Vidya Mandir from Belur. He done his PhD from University of Calcutta, and I am very happy to say that he completed his PhD under my supervision, and there is no doubt that he is one of the best students that I have ever produced as a PhD scholar. So without any further delay, may I now request Dr. Shobbhusachi Dotto to start his presentation, and the stage is yours.
Thank you, sir. Thank you for the wonderful introduction. So I'm going to share my screen and just let me know whether you can see. Okay. So if I So is it visible?
Yes, visible.
Okay. Okay, so thank you everyone for joining this talk. So I'm going to talk about, so we had a long discussion, like Angshuman and me. So about what topic to choose for this presentation. So finally, what we decided was to talk about something which is perhaps can be comprehensible to maybe the first year undergraduate students also. And also it will give a nice introduction to the subject, as well as maybe I hope that some students will feel motivated to study along this direction and pursue this direction further. So let us begin. So I am Shobbhusachi Dotto, and I'm from University of Calgary. So I'm currently working here as a postdoc fellow. And so combinatorial designs, I actually studied it to a certain extent during my PhD process. And I did some applications of it to have some nice secret sharing schemes, which actually needed some combinatorial designs to actually realize them. So, okay, so let's begin. So what is a combinatorial design? So this is the most widely spread notion that it is that is considered by researchers in this area. So it is the study of arranging elements of finite set into patterns according to some specific rules. So and there is a huge interplay with group theory, the theory of finite fields, as well as number theory, graph theory, etc. So there is a lot of interplay between combinatorial design theory and these other aspects of mathematics. And the history actually traces back to like 18th century or maybe 19th century. So when people used to do this kind of combinatorial stuff as recreational activities. But it saw a renewed interest during the early 20th century due to its heavy application in the field of statistics, particularly in the field of agriculture. So where you really want to test whether, so suppose you have two varieties of wheat, and then you want to test uh, there are three varieties of maybe fertilizer, and you want to test which wheat crop does better using which fertilizer. So there are kind of interactions between the seeds of a particular kind and the fertilizers, type of fertilizers. So so it got a huge attention, and then actually combinatorial designs, it flourished like nothing. And then and like, so like, for the last 30 or 40 years maybe, it has grown so huge, and so the field has become so enormous that it is impossible to cover even maybe the 5% of the topic, uh, but let us try. And also in modern age communication systems, particularly in computer science, it has found many applications, for example in coding theory, cryptography, so that we actually use in a day-to-day basis, knowingly or unknowingly. So what I decided is that it will not be worthwhile about giving a huge flow of information and then say that these kind of combinatorial designs exist, and then they can be created from several other combinatorial techniques. And there are so many combinatorial designs, there are so many aspects of it also, so it is impossible to cover everything. So what I decided was to uh, motivate the study with simple two examples, and then maybe go into designing some combinatorial designs which can be done with the help of undergraduate mathematics, simple algebra and nothing else. No other tools is needed. So okay, so first motivating example could be this. So when two-person communicate uh, in real time, and in particularly in present, so a sender sends a message M to the receiver. So the first question that arises is that how can the receiver be sure that the message is actually sent by the sender? So for example, when you receive, so for example, suppose, so we have seen this, you have seen this during this COVID last 2 years. So is that when you were writing exams and your professor sent the questions to you, and then you tried to answer them, and then send back the answer script, the scanned copy of the answer script to the professor. So how do you know that actually the professor has sent you the question paper and not somebody else? So I mean, the problem was solved. I mean, like, you know that since you have received the question paper from certain email ID, so you know that, okay, so since this email ID can be accessed only by the professor, and so the question paper that he has that you receive is actually sent by the professor, because nobody else can access his Gmail ID or email ID. So now the question, so here the question is kind of same, that when the sender sends a message M, and there is a receiver in between, and there is an adversary in between corrupting the channel. So suppose the sender sends a message M to the user, to the receiver, and adversary in between changes it to Q. So how can the receiver be sure that somebody has not changed the message during the transmission. So this is the first example. So, and there is the second example. So this is called wireless sensor networks. So sensor nodes are small electronic devices which have very limited computation and communication capabilities. So they are distributed in a random manner in a possibly hostile environment to gather data and then signal back to the authority that something is happening in that area. Since the sensor nodes are too small and they don't have any external power supply, so they should, I mean, we have to guarantee that they should consume as little battery as possible. So now the question is that how come two sensor nodes communicate with each other? So assume for the time being, just assume that two nodes can communicate if they have some common secret key. So if they have a common secret key between them, then they can communicate. If they don't have a common secret key between them, they cannot. So now the question is how to install how to install these keys in every node before the deployment. So this is called the problem of key pre-distribution. Okay. So now one would say that, okay, this has a very easy solution, that you install the same key in every node. So what is the problem there? The problem is the sensor nodes are deployed possibly in a hostile environment. So an adversary can capture them. So if there is only one key, an adversary captures just one node, then he can extract that key, and then the entire communication process is compromised. So he can see that what messages are sent between the nodes, and he can also send message posing as that particular node which he has already captured. Okay, and other solution is like for any two nodes to keep a secret key. So for like in the example on the left hand side, so suppose we have a scheme where A and D have a common secret key, A and B also have a common secret key, AE common secret key, and AC common secret key, etc. So for every two pair you have a common secret key. But you can see that if the number of nodes is very large, then there has to be like, so every small sensor node has to contain at least n minus 1 keys, which is impossible because they don't have that much of memory space. Okay. Now let us just look at this example just to clarify a little that. So suppose there is the sensor node A has keys K1, K3, and K5. So these keys are given to the sensor node, and B has the keys K2, K4, and K6. So you can see easily that A and B, they don't share any common secret key, so they cannot communicate. But the point is, there is a node in between E. E has a common secret key with A, which is K3. So A can communicate with E. And also, E can communicate with B through K6 because K6 is both common to both B and E. So now so in this way, A can transmit a message to E, and then E can actually then further transmit it to B, forward it to B. So this way, the communication graph is built. So now, what is the goal of this key pre-distribution is that any two nodes can talk with high probability like this link. So if they cannot talk directly to each other, then they can actually communicate through a third, maybe a third sensor node. And a random link is not broken even if some intermediate nodes are captured. This should happen with very low probability. So these are two things that one need to be careful while deploying the sensor nodes and putting keys into them. So I don't know whether this example is clear to you, or but it will be. I hope that it will be clearer when we go a little bit further. So okay, uh, let's just define what a combinatorial set system or designs, what they mean. So what says set system or design is a pair. So there is this set X whose elements are called points or varieties, and A is a set of subsets of X, which are called blocks. So uh, so X is a set of points and A is a set of subsets of X. Okay. So what is the degree of a point? A point's degree is the number of the blocks which it belongs to. And so how many subsets are there which actually contain X? This design is called regular of degree R if all the points have the same degree, which is R. And if all the blocks have same size, then this design is called a uniform design of rank K. So, I mean, you don't have to remember everything. Just remember that there is a set X of points and there is a subset. There is a set of subsets of X, which are blocks, and that's it. So, balanced incomplete block design, it is the most naturally occurring, I must say, kind of designs. Let's keep the first 2 points. So in the third point, you can see that a V, comma B, comma R, comma K, comma lambda. BIBD is actually a set system. The set is X, and the script A is the collection of subsets of X. X contains V many points. A contains B many subsets, and the rank is uniform, K, and also regular of degree R. Now, the most important part is the last one, that if you choose any 2 points, every pair of points from the set X, then they occur exactly in lambda blocks. So the last parameter lambda, it shows that every pair of points occur in exactly lambda many subsets or blocks. So there is this notion of, just becoming hazy, I don't know. Okay, so there is this concept of symmetric BIBD. So where is the symmetry? The symmetry is that the number of points and the number of blocks equal, and the rank and the degree, they are equal. Actually, one. Okay, so what I was is that give you a simple construction of using undergraduate algebra, and it is so easy that you will be amused. So let us just design BIBD where the number of points is q square plus q plus 1. So q is K. So the degree that every point belongs to exactly q plus 1 many blocks. And lastly, 1. So what is 1? That any the set, they belong to exactly 1 block. So let us go into the construction. So first you take a finite field of order q, fq. So now take the vector space, the 3-dimensional vector space. So fq cross fq cross fq over fq. Now you collect all 1-dimensional subspaces of the vector space and all two-dimensional subspace of the vector space. Okay. Now let us define the blocks. So for every two-dimensional subspace B, you define a block to be the collection of all those one-dimensional subspaces which are contained in B. So you choose. So V2 is the collection of all two-dimensional subspaces. So you choose one two-dimensional subspace, any one, and then you look at all those one-dimensional subspaces which are inside this two-dimensional subspace, and you collect them. So you do it for every two-dimensional subspace, and then you lastly declare that okay, this script A, which is the collection of subspace space V2. So now, so this is the definition. So these are the blocks, and what would be the set X. So let us see whether anyone can tell me. So, okay. So let us first see that there are in the zero vector from it. Then, and you take all the collection of all such one-dimensional subspaces, and then you throw away the origin from everyone, origin or the null vector from everyone. Then it actually gives you a partition of zero, because we have thrown out all the zeros. So it partitions this set. So now what is the, oh, sorry. So there should be this is not V1, but it should be the cardinality of V1. So now it is easy to see that cardinality of V1 is actually, sorry. Now it is easy to see that the cardinality of V1 is actually Q square plus Q plus 1. And also you can see that if you choose any two-dimensional subspace, the size of it is actually Q squared. And then you partition this two-dimensional subspace B through one-dimensional subspaces and throwing away the null vector. So it will give you a partition of B minus the null vector. So then you can see that it's an easy calculation, that you can see that every block, so AB is a block. So how many elements does a block contain? It contains Q plus 1 many elements. Okay, fine. And then lastly, that we have to show that any two pair of points. So here, now you have understood already, I think, that here the points are the one-dimensional subspaces, right? So now if you take any 2 points, so in other words, any two one-dimensional subspaces, then they should belong to exactly one block, right? And how is it guaranteed? That if you take any two one-dimensional subspaces which are not equal, then they actually uniquely define a two-dimensional subspace. And, and that's it. So this is a very easy construction of a symmetric BIBD. This is also called a projective plane. So I will not go into any more detail of it. So now you can see that this is such a easy construction method for the construction of BIBDs, symmetric BIBDs, with certain parameters, of course. So now let us come to another type of combinatorial designs. So these are called orthogonal arrays. So an orthogonal array is actually, so an orthogonal array with parameters k and n is an n square cross k array. So there are n square many rows and k many columns, where the entries are coming from a set with n symbols. And the main part is that if you choose any pair of symbols every ordered pair of symbols from the set X occurs in exactly one row of A. So for example, so suppose we choose maybe the second, sorry, the second column and the fourth column. Now you take any ordered pair. So suppose uh, 1 comma 2. Let us see if it occurs anywhere. 1 comma 2. 1, yeah, here it is. 1 comma 2. And it appears exactly once. So you can check, like for any other tuple, any ordered pair of symbol, they will occur in exactly one row of A if you fix any two column. Now the question is that it is an observation that can we see how many times a symbol, say 2, occur in any column? In other words, if you fix a column, so suppose you fix the third column, in how many rows does this symbol 2 appear? So you would see from the definition of, you would see from the definition of orthogonal array that it would occur exactly how many times? 1, 2, and 3. 3 times. Not less, not more. Every symbol will occur in a particular column exactly n times. Okay. Now let me give you a very simple construction of orthogonal array using undergraduate algebra. So you choose a Q, which is a prime power. So for the time being, you can suppose that it is a prime. And choose k many distinct elements from that field FQ of order Q. And then you define two vectors. The first one is V1, which consists of only one. And the second vector consists of A1 up to AK. So these are two K vectors, K tuples. The entries are coming from FQ, the finite field of order Q. And these are K tuples that we have defined. Okay. And through these two vectors, we shall construct an orthogonal array. So A1, A2, AK has to be distinct, and that's all. That's all you need to choose. So now you can define an array whose rows are indexed by, so how many rows, just a second. So if you go to the definition, how many rows are there? N square many. Okay. So here, the rows, number of rows should be Q squared. So how do we index the rows? So we index the rows by the tuple ij. Ij denotes the index of a row, and ij is coming from fq cross fq. So how many choices are there? Q squared many. So there are Q squared many rows. And the I comma jth row. So the row that is indexed by ij, this tuple, is actually a linear combination of these two vectors, I times v1 plus j times v2. So you can see that the entries of the array of the matrix is actually I plus j a1 up to I plus j ak. Okay. Now we have to show that it is indeed an orthogonal array. So for that, what we need to show? We need to show that if you choose any 2 points from FQ, from the set, then, and you fix 2 columns, then they will appear in exactly one row. So what we need to find is that, is there any unique row ij such that the ijth row and cth column is X, and the entry at ijth row with dth column is Y for some columns C and D. So now you can easily see by the construction that it is equivalent to solving these two equations, and it's an easy solution. So J is X minus Y times AC minus AD inverse. So everything is happening in FQ, mod Q. And once you have J, then you can solve for I. So now you know that there is at least one row I comma j which contains X and Y. And the uniqueness is obvious because of the inverses solutions. Oh my God. Okay, so lastly, I will just talk about this transversal design. So this is a particular type of orthogonal designs, and this is also is a set, and there is a partition of the set into some parts which are called groups, and A is a subset of is a set of K subsets. So every block, every subset of X is actually a K subset. That means every subset contains precisely K many elements, and it should satisfy these two properties. So the first one is okay, but the second one is the important one, is that every T elements of X from different groups occur in exactly one block of A. So this is a simple construction of transversal design, and it again uses simple undergraduate algebra. That so you define the set to be 0 up to k minus 1 cross Zp, and for every ordered T subset, because we have to guarantee what we have to guarantee that every T elements of X from different groups occurs in exactly one block. So you choose an ordered T subset C. So this C is a vector of elements. The elements are coming from the finite field Zp, and then you define a block with the help of this C. So a block AC is what? It is nothing but an evaluation of a polynomial at the point X, where you choose X from X. So you choose every X and you get evaluation of the polynomial defined by this C. So the C denotes the coefficients of the polynomials, right? So C0 x to the power 0, which is just C0 plus C1x plus C2x squared, etc. So now and then you define that the collection of all blocks is this collection of all ACs, which are the point and the evaluation of the function, polynomial function at X. Then you can see that it is a transversal design. I will not go into the calculations because it's a tedious one. But the construction is easy. That is the whole point. So if you construct, if you just spend a little time, then you can actually see that you can have the blocks of this type where I have taken ZP, Z modulo 5, the finite field to be Z5, K4, and T2. So you can actually have some hands-on computation, and then you can actually find this. But that's fine. So let's. So we have seen in three easy constructions of combinatorial designs using just very basic algebra. So let's now just see whether we can answer the questions that we posed at the very beginning, the applications of through the applications of combinatorial designs that we have constructed. We have some constructions of easy constructions of combinatorial designs, and then let's see whether we can apply them to have some good applications in the real world. So just recall what we were talking about the authenticated communication. So the sender sends a message M to the receiver, and how can receiver be sure that the message is actually sent by S, the original sender, and it is not sent by somebody else, some adversary lying in between. So now there can be two types of uh, attack on this system. So this adversary can himself pose as the sender, and then sends a message and said, oh, hi, I am actually that sender that you were expecting to send you a message. I am that sender. And the receiver says, oh, okay, I don't know, maybe you are that sender. And the other attack, which is called substitution attack, which actually does what? That the sender sends some message M, but in between the adversary sees that message M and then changes it to some other message Q. So now we want to make sure that the receiver actually identifies that something mischievous has happened in between the transmission. So let's see how we can solve this problem. So this kind of problem is solved by through this the notion of authentication code. So an authentication code is actually a four tuple such that these conditions satisfied. So S is a finite set of messages. It is also called source states. A is a finite set of authenticators. K is a finite set of keys. So you need some secret key in order to have this kind of authentication. And for every key, there is this authentication rule, EK, which is a mapping from the finite set of source states to the authenticators, to the finite set of authenticators. So how does it work? So the sender not only sends a message M, but it also chooses a key K and then apply this mapping EK on the message M that it wants to send, and obtains what is called an authenticator or a tag, and it sends this tuple M comma A to the receiver. Now what receiver does is that it actually verifies whether whether this condition is satisfied. What is the condition? That so the receiver also has the key K, so it just verifies whether the function EK applied on M gives back the authenticated value, the authenticator. So if this condition is verified, then the receiver says, okay, I accept this message as a valid message sent from the correct sender. And if this verification does not pass, so that is EK evaluated on M is not equal to A, then the receiver actually rejects that. He thinks that there must have been something mischievous happening in between the channel, between the sender and me. Something is happening there. Okay, so let's use a very easy tool for this authentication method. So what we have already seen, a construction of orthogonal array, right? So we use an orthogonal array for this authentication purpose. So let's just a second. Let's go back and see definition of orthogonal array. Yeah. So the orthogonal array has n square many rows and k many columns. Entry of the matrix is coming from the set with n symbols, such that any two columns, within any two columns, every ordered pair of symbols occur exactly once, in exactly once in a row. Sorry, not exactly once in a row, but exactly in one row of the matrix. So let's use this to have an authentication mechanism. So how do we do that? And also, okay, so let me just remind you that uh, this orthogonal array is known to everyone. Okay, so that you have to assume for the moment that uh, the orthogonal array that is used by the sender and the receiver, it is known to everyone. The construction is known to everyone. So for example, if we have this construction rule, then if the sender and the receiver decides that we will use this particular orthogonal array where the set is actually coming from the finite field of fq. So if you fix the k and the q, then you have the exact construction of the orthogonal array. So everybody knows it. Everybody. Okay. Sender, the receiver, the man in the middle who is an adversary. So everyone knows it. The construction. In other words, everybody knows the orthogonal array. There is a mechanism for authentication. So suppose B is an orthogonal array on the underlying set is 1 comma n, and suppose S is the set of messages which is up to 1 comma k. So the set of messages 1 to k. Okay, so now you would say that what kind of messages are these? That I don't want to send one to the sender does not want to send one or two or three these values to the receiver. Maybe the sender wants to send do it or do that or do something else, etc., to the receiver. So let us assume that there is some kind of one-to-one mapping from these sentences to this set of numbers. So for example, the first number, maybe this is the message, do this. The second message is to, it represents do that. And maybe the third one is do something else, etc. So there is this rule which is known to everyone, okay? And and there is this A, which is the set that we have taken, 1 up to n. And so K, so we know that orthogonal array has n square many rows. So we denote K, uh, but what we have seen here is that this. So here, the keys are actually what? The keys are actually index of the rows. So the first, if the key is 1, then it points to the first row. If the key is 2, then it points to the second row, so on and so forth. Okay. And what are the entries here in this orthogonal array? These are the entries from 1 to n. These are the elements from the ground set. Okay. Now, what the sender and the receiver does is that they meet sometime earlier and they fixes a key at random. So they choose a key from the key set randomly, and then they say, okay, you keep this, the sender and the receiver both keep this key with them, and it is a secret quantity that is only belonging to the sender and the receiver, and nobody else knows it. So what? So in our in the language of design, in this picture, you see that what they have agreed upon, the sender and the receiver, is actually a row, because every key corresponds to a row. It is an index of a row. So what the sender and the receiver has as a secret information between them, which is common to them, is the row, which row they are using during the communication. Okay, fine. So once this setup is done, now let us, oh, okay, sorry. So let us again, so these S, so we have discussed it, that S is the finite set of source states or messages that the sender wants to send to the receiver. So, so these are the messages that the sender wants to send, all possible messages. So we identify a column with the messages. So, so this, if the message is M that the sender wants to send, then actually this M is identifying this particular column. And we have seen that K is a common information between sender and the receiver, and nobody else knows it. So what the authentication rule is for every K, so this is the message that the sender wants to send. And what is the authenticator? The authenticator is this entry of the orthogonal array. So if B denotes the orthogonal array, then the entry indexed by this kth row and mth column is the authenticator. Okay. So now, so here the sender is actually sending a message that is the index of a column and the authenticator value, which is the value in this box. Okay, in the blue box. So the sender sends M and the blue box, the value of blue box, to the receiver. Okay. Now let's see whether if we use this particular design of authentication, then what is the probability that an adversary impersonates the sender and sends a value M prime and a red box, the authenticator value corresponding to M prime, to the receiver, and says that, hi, I am the original sender, and this is the message, and this is the authenticated value. Please accept. So how does the receiver know that it is not the correct sender who has sent it? It is rather an adversary who has sent this M prime and the red box. So now we just think about how the adversary wins. So the adversary wins if it has chosen a column and the corresponding value in the kth row. Because when the receiver sees, suppose the second number 2. Number 2 comma this entry k comma 2th entry, then he accepts, because he has no other way to verify, because he just sees that, okay, the second column and this particular entry matches, because he knows the k, so he just matches with the second entry, and he knows, okay, the value matches, and so it must be sent by the correct sender. Okay, so now how do we compute this probability? Can anyone say what should be the probability of this impersonation attack, that uh, actually adversary successfully cheats the. There are n square many rows, so it will, and k is just one of them. So all possible choices to the adversary is actually what, n squared. And how many? So if you fix a column, so the message is chosen by the adversary. So if you fix a column, and then how many times does this number occur in in the how many times does it occur in the number of rows does it occur to? So we have already seen that it occurs exactly n times. So the probability would be n by n squared. So that is 1 over n. And the adversary actually substitutes it through by a garbage value m prime and a red box. So now here the calculation will be a little different, but again the receiver will be deceived by deceived with at most probability 1 by n. So this is just a little bit of calculation, and that's it. So let's not go into details for this. So I have, what is the time? It is almost time, right?
You have 5 more minutes.
It's okay. So I will just wrap up now. Yeah. It's, yeah. Okay. So I wanted to discuss about this also, but then I realized that it won't be possible for me to explain this wireless sensor networks problem with this within this period of time. So what I would request, if anybody is interested, can contact me through my email. So Anshuman can give you my email ID. So you can actually construct this the transversal design 2 comma k comma p. So and see how the nodes can actually share a common key. So just recall that. So we would be creating a transversal design with parameters 2 comma k comma p. So just recall that there is this construction transversal design, and here, so we will have only a linear polynomial here. So like c0 plus c1x, and if you are really interested, then you can actually compute it by hand, taking p to be like 5 or 3 or whatever, and then see how the blocks look like this one is the kind of uh, computations, and then can see that, okay, so these nodes actually share some key, and these nodes do not. So and you can actually compute how many nodes share a common key. So let me just end my talk here. And so these are two wonderful books. Uh, uh, One by Douglas Stinson. Uh, so, and then there is another one which is by Street and Street. The second one is more statistics oriented, but it gives you a very nice introduction to the subject. And the Douglas it explores all the details one by one, and mostly uses uh, algebraic technique to build combinatorial designs. So uh, it will be okay. Let me finish my talk here. Thank you very much.
Thank you, Shobho, for your nice lecture. It is really nicely explained. So, any question or comments? If don't hesitate to send him over email, or you can contact Anshuman or me, so that I can
Yes, yes.
also communicate them the same.
Yeah, sure.
So, thank you very much, Shobhushachi, for your time and all efforts towards this presentation. Thank you very much.
Thank you very much.
Yeah, so we are here. I mean, we are happy to say you that the second speaker of this one-day international seminar on mathematics and its application, Dr. Rajat Shubro Hajra, is already amongst us. So he's already there. Welcome you. And it's my great pleasure to introduce him as well. So Dr. Hajra is currently an associate professor at University of Leiden, Netherlands. Prior to this, he was an associate professor of mathematics in Indian Statistical Institute, Kolkata. He had completed his bachelor's from St. Xavier's College, Kolkata, and his master's from the Department of Pure from Indian Statistical Institute. He has been awarded with many prestigious awards like Young Scientist Award by INSA as well as International Indian Statistical Association. More importantly, he is the Shanti Swarup Bhatnagar awardee in mathematical science section, and it was awarded in 2020. His research interest includes in extreme value theory, random matrices, and random graphs. And we are very fortunate that he is amongst us, and he is going to talk about the lectures on random graphs. So without any further delay, let me invite Rajat. Please, the stage is
Uh,
yours.
uh, so am I audible?
Yes, you are audible. Yeah.
Okay, so I'll start sharing the screen perhaps. Uh,
I think computers on or
yes,
continuous screen, maybe.
is it causing a problem?
No, it's
Do
fine.
you?
It's fine. Yeah.
No,
Thank
it's
you.
fine.
Yeah.
Okay, okay. So hope you can see these slides, right?
Yeah, it's visible.
Yes, yes, yes. No, no. Yeah, I had to put two setups because I generally in Google Meet I don't see how people are or what people are saying generally. Firstly, thanks Abhishek for the very kind introduction and very nice words. And thanks everyone for attending this talk also. And thank you Sobo for the nice talk you gave. And I guess it's time for you to sleep now. And for me, it's morning. And India, it's afternoon. So we are in three time zones here,
Yes.
listening to the talk. Okay, so coming to the talk, uh, uh, as Abhishek das said that I'm now in Leiden and I was in Calcutta for a very long time. I did my PhD, Masters, BSc, everything. So in 2021, I moved to Leiden, and which is in Netherlands. And now my main focus is on random graphs, random networks, and that's one of the things I'll be speaking about today. I don't know how the questions go, but if you have any questions, please try to unmute yourself and speak, and try to stop me if you need any questions. So okay, so as you can see in the title slide, there is a lot of colorful pictures. One of the pictures you see this, the first picture is of a uh, It's taken from Facebook. So this is the Facebook network picture, which is shown in the blue there, and here you see on the side, one side is a histogram plot of a very sparse random graph. So that's how that's the talk is about. So what we'll try to see is how to link these pictures to spectrum. Okay, so what's this talk about? I believe most of you are undergraduate or master students, so many of you might not have seen random graphs or even had a course on graph theory. So I'll keep this thing in mind, and also things like I'll not go into too much technicalities of probability also. So the only technical thing I need is some basic probability and some linear algebra, like eigenvalues and eigenvectors. So most common network nowadays we see around is social networks. So social networks is one of the biggest networks we have now. For example, Facebook, Twitter, Instagram. And what does the word network mean? Network just means that it's a it's a it's a sequence of graphs. So there are, say, suppose billion vertices, and there are some random edges between these billion vertices. So you can think of, so here is a these are two pictures I have taken from internet. One is a schematic of Facebook on the right, and one is a schematic of Twitter. So Twitter, for example, is a directed network. So when you enter Twitter, you will see that you can follow someone and follow the tweets. And so you are in one direction. You're so these are not really. It's very difficult. You can imagine. So India's population is 1.3 billion now, and I would say 50% of the people are now using smartphones and using Facebook also. So you can imagine the size of these networks is huge. So it's so, but what is the aim? So understanding these huge networks is quite difficult. So what we want to understand is what are the geometric properties these networks kind of give us. So there are other types of networks. So let me tell you a few other real life networks look like. So here are four examples of real life networks. So the first one you see is a traffic network where the vertices you can think of as airports, and the links are, so the edges are uh, traffic. So if a flight goes from one airport to another airport, it forms a edge. And so this is a more kind of a deterministic network. So you see, and it can happen also with railways. For example, like if you take the railway network of West Bengal or somewhere, so you can think of stations as vertices and the trains going from one station to another as edges. So these are certain kinds of spatial networks because it depends on the space where you are in. So these are example spatial networks. Uh, in literature more, I would say the banking networks. So banking networks is you have two banks. Say suppose any transaction, any financial transaction between them causes an edge to occur between them. So here you see there is a banking network there with the red and black, and uh, so the dots are banks. So for example, it can be uh, so you can form networks in many ways. For example, if you take the State Bank of India, you can take all its branches. So there is a central branch and there are sub branches everywhere. So any transaction between the sub branch and the central branch will cause an edge. And you can also consider intra banking, in which you have like SBI, HDFC, other things, and any transaction will give you another link. So this is an example which is of a Brazilian banking network. And then there is also biological systems. Biological systems means protein-protein interaction in your body forms network, and they are beautiful looking. So if you look for in the internet how does a protein-protein network look like. These are some of the sample pictures, and they have certain characteristics. So you can see that there is some kind of symmetry. There are certain properties like trees appearing. Problem is, mathematically, how do you describe these things? Another network which I like a lot is actor network. So here the vertices are actors, and the edges are if two people have acted in the same movie. For example, you see there is Robert De Niro, Brad Pitt, Tom Hanks, Leonardo DiCaprio, Matt Damon. So you see there is a big node for Tom Hanks because he has done so. One of the movies is Saving Private Ryan, which had a huge crew in the movie, and that's why he has a huge node. That means there are lots of edges which are coming into the node uh, of this. So there are lots of edges which are entering this node. So that's why these are big networks. Uh, you see there are big dots there. So these are people who have worked in with many people in the movie industry. So there is no graph as such for the Bollywood ones, uh, or at least I don't know of anybody who has done this study for the Bollywood actor network. But it would be interesting also. I think some of the small actors might be having a huge chunk in them. So maybe like someone like Amrish Puri or one of the villains would have a big chunk in it. So okay, so these are some real life models, as I said, and so what is the target of us? So we are kind of mathematicians. We want to think of how to model this and how to study the properties of these real life networks. You see these nice pictures. You can do a lot of computer science things with that, but for us, it's more of the mathematical questions we want to ask. Okay, so to study mathematical questions, you have to understand what are the so you cannot list down every property of the network. What you have to do, you have to choose and select. Say you have to choose certain properties of the spaces and try to model them. For example, like that's what you do in mathematics. So if you study a say a topological space, you want to tell what are the characteristics it has. For example, like in a standard class, that's why you start with what is the definition of compactness, what is the definition of connectedness, what is the definition of path connectedness. So these are basic properties of a space you want to learn about. And random graph is certain things. It's not standard. So it's a discrete space. You have discrete space of points. So just studying compactness or certain other properties doesn't help. So you have to find some basic properties which help you in understanding what the networks is. So what does the physics and the computer science literature suggest is there are three characteristics of modern social or modern networks. So let me so as I said, there are various challenges. So computer science observed that there are three kind of very characteristic features of real life networks. One is this is what is called a scale free. I'll tell it to you in a very intuitive manner. So the observation is the degree distributions are of power law. This claim. Power law. So what does that mean? So this means that what is the chance? So in the chance here means what is the probability that a vertex has k connections? So you ask this very simple question that you have a given network, you have a given set of vertices and edges. So what is the chance that a person in the network has k friends? So the physicists conjecture that in real life networks like this probability is like k to the power minus alpha. So if you tell me that what is the chance that you have 100 friends, then it's like 100 power minus alpha. And if you say it's 1,000, then it's 1,000 power minus alpha, which becomes smaller. So but the decay of this is always is like a power law. And one of the important targets of physicists, computer scientists, everything is to determine what is this alpha. So let me give you for if you look at uh, so Facebook. So if you go to the Facebook website, so I'm not saying the social media website, but the Facebook informations. So they estimate this alpha is between 2 and 3. So I think it's now uh, somewhere between 2.7 or something like that. So but it keeps on decreasing now for them, and but it's always more than 2 for the moment. The actor network is more tricky. It's between 1 and 2. So people know how to determine this empirically now. So there are huge machines, huge supercomputers, AIs, to determine what this alpha is. So this is one of the crucial points. Second geometric property which people observed in these networks is that if you pick any 2 points in your network, it takes a very little time to reach from one point to the other. And this is called the small world phenomena. So small world phenomena because the world, so what is it saying? That it's saying that the world around us is becoming smaller. Just as you see, like this is today, what you are seeing is a small world phenomena. So Shobhosachi is giving from Canada, I am from Netherlands, you are sitting in Calcutta. So so this is becoming really a small world. So although there is huge distance, but there is a medium in which we can reach each other very instantaneously. And so this is a feature of any network. Uh, and and one of the key points is the people in your department or the teachers in your department know some of these people, some of us who are outside, so they can contact you. So you are contacted by your teachers, the teachers contact us, and we now get in touch with you. So it's just, so if you think of all the students and teachers as a graph, so you are at only distance 3 from us. So it's a so maybe I reach Onshuman reaches you, so it's a distance 2, for example. So in the graph, so the distance here is the graph distance. So you travel between one vertex to another and one vertex to another. So you just calculate the graph distance. So this is what is a small world phenomenon is. Another thing is what people observed, which is kind of still mathematically very challenging to study, is it has been observed that there are large clusters in your networks. So if you remember the pictures I showed, so there are huge clusters around certain people. For example, if you see the whole world Facebook users, uh, you will see that Brazil and India are the only two countries which has a very dense cluster of Facebook users. Not even US, although Facebook has a center for US. So one of the reason is, okay, so these are all advertising reasons, social marketing reasons. So India and Brazil are moderately growing economies, which has huge amount of infrastructure which is being put at a very cheap cost to everyone. So everyone now has phones in India, and smartphones in India, and somehow you see there is a huge cluster of users which start appearing in your network. So this is one characteristics of social network, and understanding how these clusters behave is a challenging problem. So these are all physics and computer science conjectures, which are or properties which we take. So, but if you tell me like how to start modeling this, so there are a few models in mathematics which can imitate a real life. So mathematics has been like this. If you think of like we have been doing mathematics for now thousands of years. Most of the problems, if you think even 200 years back, came from real life problems. Now we have moved. So when we see some uh, problems, we forget about these real life problems and say that okay, we like abstraction. But most of the mathematical problems has roots in real life problems. And same, so if you see, the network science also has real life problems, but when it comes to doing mathematics, rigorous mathematics in it, so there are only few models. So what I'll be showing you now is there are uh, three mathematical models which are now well known and people have studied. One is Erdős-Srény random graph, another is called a configuration model, and the last one is the preferential attachment model, which is also called the Albert and Barabasi model. So, let me go to the description of these models. Okay, so here is the first Erdős-Srény random graph model. So here are two pictures. So the person with the white hair is Paul Erdős, and the black hair is Alfred Renyi. Both are Hungarian mathematicians, and I guess most of you have heard at least Paul Erdős's name. Uh, if you haven't, you should go back today and start reading about him. He was one of the most prolific mathematicians of the previous century, and the biggest story goes that he always had his suitcase packed. So everywhere he went, like, so he was never, so he did not have a home. So he was just traveling with one suitcase to different collaborators, just collaborating and working and staying there for a few months and then moving on to another collaborator. So he was always traveling like a vagabond. And and he produced wonderful papers. So this is one of the random graph models which was proposed by both Paul Erdős and Alfred Renyi. Both are Hungarian mathematicians. Today in my talk, you will see that there are lots of Hungarian mathematicians. One of the reason is uh, that Hungary is one of the topmost countries in if it comes to combinatorics, and they are the leading there. Like still, they are the leading. So this year, by the way, like we people are in fact, it was previous year. So people started celebrating Alfred Renyi's 100th year. So we had big conferences where it was organized. So here is a nice picture of Erdős's collaboration network. So this is uh, so this is so there is somewhere Erdős, but all the other dots are his collaborators, and there is a huge link between the collaborators themselves and this Erdős. And so if you look at a larger network, so people try to connect and get what is the Erdős number, for example. So I don't remember my Erdős number. It's perhaps two or three. So Erdős number defines that how far are you in collaboration distance from Erdős. So say for example, if I collaborate with someone uh, and that person has collaborated with Erdős, then my Erdős number would be just 2, because I'm just at a 2 distance in the graph. So this is, so how to describe this model is uh, so what you do is you start with n points, and this I call the vertex set. V is 1 to n, and you fix a probability p, which is, so a parameter p which is in 0, 1. So these are, as you can see, this is a picture where you have n points, and what you do is first fix a p in 0, 1, take any pair, toss a coin, and say it lands head with probability p and tail with probability 1 minus p. So if you toss a fair coin, then it will toss, so if p can be half also, then it's a fair coin in the sense that it can be head with probability half, it can be tail with probability half. Now you pick any vertex, any pair I and j in your graph, and then you toss a coin and see what is the outcome. Say if it lands head, then you put an edge between them, otherwise you don't put an edge. And you do this independently, so your tosses shouldn't depend on what you defined before, and you do this independently for any ordered pair. So here is a graph, as you can see in the picture. So here is a graph of 20 points, so a vertex set of 20 points. I have picked a few edges already where I have tossed the coin and they have landed head. So there are 4 already heads on my list. But what I can do is now I run a simulation here, and the computer does the tosses for me. And so the computer is doing it very fast. You see, the computer is doing it very fast. It's taking all the pairs, but you see only the edges which are appearing by the tosses, so which are head. So you don't see the tails, because when the coin lands tail, you don't actually see the edge because they are not being put. And so this is a structure. As you can see, it's a graph on about 20 vertices, with p being 0.1. And so you see there are certain properties. So there are some isolated vertices. So for example, these are some isolated vertices which are lying around. There is a cycle also here. For example, there is a small square which is appearing. So and there are not too many edges within the graph. uh, so hope this graph construction is clear to everyone, because this is the graph which I'll be studying today. Okay, so before studying this graph in more details, let me go to describe you what happens to the configuration model. This is the most modern model, one of the most modern models which has been studied. So, so the idea is, computer scientists do experiments. They say, okay, I'm looking at a huge network, and I have a vertex set of 10 billion, and I have huge data. So what data do I have? I have a data which says that the degree distribution of, so the degrees, possible degrees of this 1 billion people is given to me. Can you give me a random graph? So random in the sense it's a random thing you have to do, and which matches this set of vertices and this set of degrees. So let me give you a small mathematical example. It's a non-trivial example to think of, because it's not. So what is the mathematical problem which is you have? Say you have 5 vertices. Let me call these vertices 1, 2, 3, 4, 5, and I give you a degree sequence. I say my vertex number 1 has degree 2, my vertex number 2 has degree 4, my vertex number 3 has degree 2, my vertex number 4 has degree 3, and my vertex number 5 has degree 1. Can you construct me a random graph with this degree sequence? In this particular example, due to some, because I have chosen it in a particular way, you can do it, but it's not always possible. And this is a very difficult theorem in mathematics, which is known by the name of Erdős-Galai theorem, which gives you a certain condition under which you can draw this graph. So let me try to point out how to draw this graph. So what is the question? So here is the construction. So I have 5 vertices. So what I do is I take vertex 1. I know I need degree 2. So what I do is I draw 2 edges to it on this vertex. And I call this half edges because I'm not completing my graph. I take the second vertex. I know it has to be degree 4. So what I do is I put 4 half edges to it. I take my vertex 3 and put 2 half edges. I take my vertex 4, I put 3 half edges, and I take vertex 5 and I take 1 half edge. Now I have to construct with this picture, I want to construct something random. So what I do is I pick one of the half edges. I pick the one with 1 and the first one which is there, and I connect it to uniformly. So I choose from the remaining people, remaining stubs or remaining half edges, I choose one uniformly. So what I do is from any of them, I choose randomly one of them. So for example, my vertex 5 connects to this in the first one. Now I go to the second stub. So this randomly chooses number 2. Now I have the next one. This chooses the neighboring one. This is a possible choice. Now the next one goes with the 4, and this is going with 3, and this is again going with 3. So what you see is I have formed a random graph by this uniform choices. You can calculate the probabilities exactly of this, of what is the probability of this graph appearing. But the important feature is, you see there is a self loop in this graph. In the sense, there is an edge which connects to itself. So, and there are multiple edges. So for example, what is multiple edges? You take two vertices, they will have multiple edges between them. So this is one of the construction. Let me show you how the computer does it. So, mm, so, so, okay. Simulation. So I have 20 vertices, and I give maximum degree 6 and minimum degree 1, and ask the computer to perform this. So what it does is it draws some half edges on these vertices, and it chooses uniformly any pair and connects with them. So this is what the computer will start doing. So it will start connecting with itself. Since it's considering all the pairs, so it takes a bit of a time, but still it's quite fast, uh, as you can see. So here is a graph which is formed, and yes, this is the final outcome of my graph, which comes out by this uniform. So, so what was my ingredient? So the ingredient was, I was given a set of vertices. I was told that from my empirical study, these are the degree sequence. I produced you a random graph which exactly corresponds to that degree sequence. So, so this is one way of constructing, and this is a very good way, because somehow there are experimental data now, and you can construct certain properties. But studying geometric properties of this graph is still quite a challenge. Now there are methods, now there are techniques to study this, but this is still a challenging. The preferential attachment model has a different mechanism. So as you see in the last two graphs, what did I do? I had my vertex set fixed. Now, if you think of modern networks, uh, the vertex set fixed is not good. In a sense, say you are you have the Facebook network. You know someone you met on the street today. You say, you are not on Facebook. Please join on Facebook. So he comes to the Facebook network. He joins, and so he creates a new vertex in the graph. And what does he do? So he tries to find a friend who he knows has lots of friends, so that he can connect with other friends. So what is it doing? So there is a new graph which is entering the graph network, and he's trying to find some vertex which has a very high degree or very high connection. So this is an example of a network which is growing in time. So every new vertex which comes with some new number of edges, and it tries to connect with vertices which have very high degrees. So this is what is called a rich become richer. Why? Because if you have lots of friends, you attract more friends in your model. So this is a very uh, socially relevant model in today's world, because this is what is happening today. The rich becomes richer, the poorer becomes poorer, and that's where we are going towards a society as a way also. So this is even in not going into the economic terms, but also in the terms of social networks. So here rich means you have lots of connections. So people with lots of connections, they tend to get more connections. So what is happening at a single time n, a single vertex, a new vertex is added to the graph with m many edges. So you come to a party with m friends, and you try to connect, and these, and you and your friends, m many friends, try to connect with the original existing one. and you generally connect with the probability that is proportional to the degree distribution. And and this degree distribution, so the degree should depend on what you were at the previous time point. So let me show you one of another video of how this goes. So you start with one vertex which has a self loop in it. So I count that as two edges. And now a new vertex came in. So, so, so a new vertex comes in with two edges. It connects to the existing one. And then slowly, every time a new vertex with two edges tries to come in and tries to connect with the graph. And you see slowly every time point a new vertex is coming in. So your graph is growing with n in a way. So, and what happens is this graph, if you see, I have plotted a histogram of, so this is, so how many vertices have degree 2? It's I have cut it out. It's number 12. Many vertices have degree 2. How many vertices have degree 3? Like there are 3 many vertices. How many degree have 4? So on. So if you look at how many vertices have degree 5, then it's like 3. So if you do it for large n, what you will see is the degree distribution of this graph has an inbuilt power law. So this is one of the fantastic achievements of another Hungarian mathematician, Baravasi, uh, who came up with this model and showed that by construction of this graph, you will see that you get an automatically a power law in the degree distribution. This is not easy to calculate, and it's not easy to present to you, but the proof is beautiful. It's a basic probability with lots of counting argument, and yeah, it can be done in one class to make it completely rigorous. So what are the mathematical questions we want to answer? So these are 3 rigorous mathematical models which kind of represent real life networks, and people have studied it for a long time. So the question is, how does the random graph look like for a large number of vertices? Uh, Again, topologically, in the sense that uh, whether there is a huge connected component in your graph, or it's a connected graph, whether you have disconnected clusters, what is the size of these clusters. So cluster means, so you take a portion of the graph which is called a cluster, means that everything is connected with everything. So you can go from one point to another without any hesitance. So you can just use the edges and go from one point to another. So think of, if you have an isolated point. Isolated point means that you are not connected with any of the edges. So that means you will not be able to reach that point if you pick from one another point. So, but in a cluster, so if I take a cluster, it means that I can reach one point to another with the help of my friends. So, so these are the questions, but how large can the cluster be? So for example, the size of the cluster became very relevant when we were recently dealing with the COVID period, when people were trying to understand how many people are infected per day. They were trying to calculate essentially the clusters in that. And one of the estimates which come in is through this random graph model. So what are the kind of phase transitions? So do you see any kind of, so if you change a parameter, do you see changes in the geometrical properties of these graphs? Then there is a question which is very important and relevant these days. In fact, last week we had a huge meeting with mathematicians, physicists, journalists, and everything. So how to tackle fake news? So there has been a remarkable, so I was astounded. So here we have an undergraduate program in Eindhoven. So graduate students came and write down a topic and people start commenting on it, and it's not really moderated. So especially in India, in some of the areas it's banned now, but still Reddit goes on in a very popular level in everywhere. but it's a place which generates a lot of fake news also. And these guys, these undergraduate students, built up a mechanism or a program. They were mathematics students. They came up with an algorithm which can detect, by running a computer, that it can alert in a proper way what is a fake news. So how this fake discussion, and this comes from the more geometrical structures. Reddit is a kind of very special thing because it releases all the data it has. So it's not like Facebook or Google, which keeps secretly all their data, but Reddit kind of declares all their data. So it's an open source kind of thing. So in the brief 15 minutes, what I will try to look at is what is the spectrum of the random graph, of these random graphs. So what I'll do is, so let me tell you what is the spectrum of a random graph is. So given a graph means I have a vertex set, I have an edge set, which can be random also. So we assume for the moment that the graph is simple. So there are no self loops and no multiple edges, in the sense that there are not, so say one is connected with with only one edge. So there are no two edges between two vertices. And one doesn't connect with one itself. And say the vertex set has size n, and we assign for every vertex, every graph, n cross n matrix. So how do we assign it? So we say the ijth element of this matrix is 1 if there is an edge between I and j, or 0 if there is no edge between the vertex I and j. So this is an n cross n matrix, because what you're doing is you're picking, say, vertex 1 and 2. You're checking if there is a edge, and and saying that, okay, it doesn't have an edge, put 0. If there is an edge, put 1. So it's a bunch of 0 1 matrix with 0 1 elements. Very simple. And it can have n eigenvalues, as you know. So eigenvalues is, just to remind you, is the, so if you solve this equation on a vector, a and v is equal to lambda times v, so lambda is then an eigenvalue of a. So the collection of these eigenvalues is called the spectrum. And eigenvectors also are important, but I'll not speak about too much about eigenvectors today. So now, as you see, as I was saying, the networks are very large. So our idea is how to solve or understand the behaviors of these eigenvalues, because eigenvalues are generally very complicated functions of the entries of your matrix. But let me give you, and as you can see, the graph we constructed was random. So the matrix is also random, in the sense that the entries of the matrix are random, because you don't know. So there is a, so when you are doing this random graph construction, so say I pick a vertex 1 and I pick a vertex 2. So I'm doing a coin toss. If it lands head, then I put an edge. If it lands tail, then I don't put an edge. So it's a chance, in the sense that it can be head, it can be tail. So there is an edge, there is not an edge. So the entry of the matrix can be 1 or 0. And so here is a deterministic example. So this is a star graph. As you can see, it has 10 points. So what you can do is you can write down the adjacency matrix. So we call this the adjacency matrix as follows. So you see the 0th or the 1th entry is 0, because it doesn't have a self loop. But there is a 1 between, at the position 1 2, and then 0, then 0 0, and there is a 1 in the first row between 1 and 10. And like this you construct this matrix, and it has a nice structure in it. It's a tridiagonal. It's a diagonal. Diagonal is 0, but the principal diagonal is 1. So if you give it on a computer, or if you do some linear algebra, this was one of our favorite matrices in Mappa's book, I think, in linear algebra, where you had to find the eigenvalues of this matrix, which is nice. You can find out what the eigenvalues of this matrix are. So, but our challenge is much more difficult. So in the sense that you don't know where these ones and zeros are placed, and you don't know how many eigenvalues are there. So one of the most difficult question which was solved few years back was, what is the chance that the eigenvalues you get, so you get n eigenvalues, what is the chance that the n eigenvalues are distinct? So can you tell me that, okay, I have an n cross n matrix, I know there are n eigenvalues, can you tell me that all the eigenvalues are distinct with certain probability, or is it with probability 1? So it was a long standing problem for a very long time. For certain values of p in Erdős-Srény, it was solved by Terence Tao and Van Vu. And later in 2019, it was solved completely in a brilliant paper in Annals of Mathematics. Uh, uh, so you can understand that how difficult it can be. Okay, so just to recall what we were doing with Erdős-Srény, so we had a vertex set 1 to n. We pick pairs, toss coins, and assign edges independently. And the probability of head is p, and this is the complement of the tail also. So what is the random variable at the ijth position? It's just a Bernoulli p. Bernoulli is so Bernoulli p is a random variable which takes the value zeros and ones. It takes the value 0 with probability p and 1 with probability 1 minus p. And the entries above the diagonal are all independent, because what I said is when you toss the coins, you do it independently. You don't depend on each other. So independent roughly mathematically means if you take any nice function of your ijth entry and nice function g of your klth entry, then the average becomes a product of these two. So this is what is independence whenever this ij and kl pairs are independent. So it's a matrix with random elements, Bernoulli entries, very easy entries, but it's a symmetric matrix because I'm not giving you an order in which you should choose your coin. So edge between 1 and 2 and 2 and 1 are not distinguished differently. So since the matrix is real, symmetric, so you know the eigenvalues would be real. So this is a very simple exercise. This is, if it's non-symmetric, then you get complex eigenvalues, then it becomes more challenging. So random means here, as those who are not acquainted with probability, just to keep in mind that random means that an outcome is uncertain. So here are some plots of eigenvalues. So I take this n cross n matrix, I have n eigenvalues, I scale them with square root of np. I'm not explaining at the moment why I'm scaling this, but to understand why I'm scaling this, you should think that just to put the picture in the because if you don't scale it, it will be very large. So you'll see a lot of, so I cannot fit it in the slide, but this is the right scaling to put things on. So you see, so I'll be slowly increasing my n's, and you see as n goes to 3000 and p is 0.01, you start seeing a pattern in the eigenvalues. So all these bars are like eigenvalues for you, and you see, so there is a clear pattern which is kind of in the eigenvalues. Now this is not a surprising pattern. This pattern was observed first by Eugene Wigner, who is in a 1954 paper, who was studying a paper, molecules of uranium-235. So he was studying this atomic structure of the uranium-235, and he saw this same phenomena at the energy levels of your uranium. So Wigner, who is a Nobel Prize winner in 1963 for groundbreaking works, he wrote a paper. So he's a physicist. He wrote a paper in Annals of Mathematics in 1954, which proved this theorem. So this is called the Wigner's theorem. So suppose P is, so I have changed the Wigner's theorem because Wigner's theorem is much more general. So I'm stating it in our setup. P goes to 0 and NP goes to infinity. So this is a condition. So if you're looking at the number of eigenvalues scaled by root NP less than x, and you normalize with total number of eigenvalues, which is n, then it converges to a function which is a distribution function. The SC denotes the semicircular law. So this red line you see in the picture on the last is a semicircle. So he proved that this, so if you look at the number of eigenvalues which are less than x, and if you scale it properly, then it converges to a semicircular distribution. So, and the density, as you see, the red line is the derivative of this distribution function, which is given by the semicircular density. So this is 4 minus x square, square root of that. So plus means it's a positive part of this function. So Wigner proved it under much general conditions because he was studying some atomic structures and everything. But he came up with a mathematical proof which is still one of the best proofs known in this area. So it was a brilliant work. Just the thing to note is these lambda i's which you are taking here are random. Because my matrix is random, matrix is random means matrix is uncertain, so the lambda i's are also random. So maybe I'll skip a few things. So why this condition that NP going to infinity geometrically mean? So NP going to infinity means roughly the average degree of your graph goes to infinity. So it's blowing up. So I'm not going into the details, but you can show that the degree of the vertex set I is a binomial random variable with parameters n minus 1 into p. So the average is n minus 1 into p, and hence it goes to infinity. So it means that at an average, every vertex of your graph has huge number of friends. So this is one of the reasons which was, so you can ask what happens if NP doesn't go to infinity when NP is converging to lambda. And this condition, okay. So what you can see, so this is, I think many of you have perhaps seen in your undergraduate, that if you take a binomial distribution, if you take the parameter p, if you put lambda by n, then using a nice Stirling's formula, you can choose that the binomial will converge to a Poisson distribution. This was like one of the basic results we learned in undergraduate probability, little whatever we learned. So as I said, the p fix means that the average degree goes to infinity, and this is not desired always. So what you want is p to be lambda by n, and then you see the average degree will converge to lambda. Now, there are three cases of random graphs you can create here. One is p going to 0, but np going to lambda. So p is, that means lambda by n. So p is going to 0 at a rate which is lambda by n. Another case, so this case is called sparse. And what you have seen in all the real life networks is many of these cases happen that huge number of graphs are sparse. Then there is a p fixed, and then there is a case where p goes to 0 but np goes to infinity. So, and each of these cases people deal with the geometry in a very subtle way. So I'll skip this slide, but I want to show you that these are some of the big peoples. I don't know how many you identify here, of the one of the famous mathematicians. So I can't show my. So on my left hand side is Terence Tao and Van Wu. People have, it's under the, so they have worked on the sparse graphs. Just beside Van Wu is Laszlo Lovász. So he's an Hungarian mathematician who has worked on dense graphs. So let me, I can't even hide it. I don't see my cursor. And beside Lovász is Charles Bourdenave, who developed the theory for sparse random graphs. On the top corner is Varadhan, who is an Indian Abel laureate. Beside him is Saurav Chatterjee. He's a big mathematician who has won lots of awards like Rollo Davidson. He's in Stanford now, from Calcutta. And in between, you see there are two pictures of Hongzar Yao, and he's another person is Laszlo Erdos. So he's not related with Paul Erdos, but he's Laszlo Erdos. So Laszlo Erdős is one of the most famous mathematicians in recent times because he solved most biggest conjectures in random matrix theory in recent times. So he solved about, I don't know, 13 conjectures in a span of 10 years, which was open for 60 years almost. So as you can see, all these different categories of graphs have huge Fields medalists, Abel laureates working on them, and each of them have their own geometrical difficulties. So it's hard to put in one picture. So just to show you a picture on how the spectrum of the sparse case looks like, the sparse case looks not very good. Uh, so you see there are extensive simulations by two phases, Bauer and Goninelli, and you see it's not shaped like a semicircular law as I was. So here you should think of alpha as lambda because I've taken the pictures from their paper. Uh, as lambda or alpha increases, you see there is a pattern which is like a semicircular law. And as alpha is small, you see there are huge spikes in them. So there is a phase transition in which the behavior of the lambda goes into this picture. Okay, I'll skip this technical result. So I'll come to the last part where we are in 5 minutes. I tell you what we are working on. So as you saw that we took Erdős Srény with coin tosses with probability p. So what was that like? This is called a homogeneous graph in the sense that so every pair of vertices had the same probability of connection. But in general, what is happening is in our networks we see community structure. So what do I say? Like, so Indians, for example, people from Presidency will have a greater chance of making friends with people from Presidency than with St. Xavier's. So the P is not the same when you consider real life networks. So the probability changes when you do different communities. So this is what we are trying to do. And so what choose any pair, put an edge independently with probability Pij, and Pij's need not be same. One example is here is an example that you put a parameter epsilon, you take a nice function on the square which is symmetric, and you put f of I by n, j by n. And let me show you pictures. So for example, the coin toss probabilities can be square root of I dot j by n into epsilon, or it can be this Pij's are indicators. So your I is less than n by 2, j is less than n by 2, and it's 1 if I is greater than n by 2 and j is both n greater than n by 2. So you see the shape of the pictures kind of change as you change the Pij's. So this is the message I want you to take, that as you change the Pij's, the shape of the pictures kind of changes. So one of the main results we proved was that if you look at the same quantity which Wigner had, uh, so what you can show that it converges to another function which need not be semicircular law, and some special cases you can identify explicitly the law. I'm not telling you what this is, but it comes from something which is called a non-commutative probability. So it's related with something which is called a non-commutative probability, and it's a multiplicative convolution of semicircular law and another distribution. And here is Dan Voiculescu, who is the founder of the free probability or the non-commutative probability, which is another big area of mathematics which is there. Okay, so I'll skip and come to the final remarks. So as I showed you one example of what the results can look like, one can also study how does the largest eigenvalue, for example, behave. What are the properties of eigenvectors? This is a very difficult problem. There are multiple open problems there. What does the gap statistics look like? I'll come in a moment on this. Uh, so what happens when n epsilon is lambda in homogeneous case? This is, we are working on more properties of this inhomogeneous graph. And I did not say anything about configuration and preferential attachment because nothing is almost known about the spectrum. So there is a wide open area which is still to be explored mathematically in terms of spectrum. And this phenomena you see in random graphs is much more universal. So Eugene Wigner, who got his Nobel Prize in 1963, so for the contribution of theory of atomic nucleus, elementary particles, applications of fundamental symmetry principles. So it might seem these are physicists. What do they conjecture about? Okay, so he suggested that solving Schrodinger equation of complex systems, blah blah blah, and then he said, look at the gap statistics between energy levels. What he was doing, so he was studying the difference between the eigenvalues and taking a normalization and plotting them. What he saw is a picture like this. Okay, very nice. This is called the Wigner's surmise. But later, some more physicists who started working on it, and number theorists, and some ergodic theory, dynamical systems, all saw the same pattern, exactly same pattern. And these are some of the examples. I would like you to see B, C, and D and E. Not the last two are the extremes, which don't have this pattern. So one is the gap between primes. So this is the, so if you plot the gap between the prime numbers, you see a similar pattern, and with number C, which is also the energy levels of a uranium 466. And the D is called a Sinai's billboard. So billiard, sorry, Sinai's billiard. It's a model which models billiard. And number E is the zeros of the zeta function, which you know is related with the Riemann hypothesis. So if you look at the gaps between the zeros of the uh, uh, zeta function, uh, it's quite related with what you see in the gap of the eigenvalues. So, so there is a big universal phenomena which is going on, which is why we need you in mathematics to explore this and understand this, because there are lots of things which we should understand. And I thank networkpages.nl for the simulations which you saw, very nice simulations. And if there are any questions, please feel free to tell me. Thank you.
Thank you, Roger, for your
Ah,
interesting talk. So, yeah, may I
uh,
request if you have any question or
yes,
question, please.
yes, I have a question.
Yes, please
Uh,
go
th-
ahead. I can hear you.
thank, hmm. Thank you so much, sir, for your informative lecture. And actually, my question is about that. What are the usefulness of studying spectrums of graphs? I mean, actually, we can say some properties from the spectrum about the graphs,
Mhm.
like bipartite graphs, etc. Then, what are the
Now, one
other
of the
usefulness?
reason is I'll give you an example why this is important. For
Hmm.
example, uh, one of the crucial information about, say, for example, let's take this algorithm which Google uses, which is called the page rank. So what you do is you give a search. Immediately you will see that there are lots of web pages coming, and there is a timer which is written in
Hmm.
0.03 seconds or something like that. So what is it happening is, what does Google do is it allows a random walk to crawl on the all the web pages and come quickly to a point which is exactly, or search few things which are exactly at your point. Now the control of this random walk, which is doing on this huge network, needs to be very fast, and the
Yeah.
control parameter exactly comes from the second eigenvalue of this matrix, which is coming from the network of web pages.
Oh.
So essentially, so so now we are advancing to one more level, which I did not want to go today. Is so so eigenvalues don't exactly give you properties much about, okay, it gives you some properties about the graph, but it gives you more properties about dynamics on the graph. So say, suppose you have a graph and you have a
Hmm.
dynamics on it, in the sense that, for example, a standard example which I give is not a nice example, is, say you have a network and you have COVID now, and COVID is spreading.
Hmm.
The speed of the COVID network, or at which it spreads, or this R number, if you remember in news or newspapers, which we always looked at. So if you take a infectious process like SIR or SIR T, the largest eigenvalue controls the rate of this. The largest eigenvalue of the adjacency matrix of your graph controls the rate at which these infections are spreading. So
Okay.
somehow all this is this. So this is one example of usage of spectrum of random graphs.
Okay. Okay. Thank you.
So any other question?
Rajat,
So
I have one question. So
Anshuman,
in the yes, so in the very first or second slide, you talk about three properties of, I mean, that
yes,
we usually find in real life graphs.
yes,
So out of that, the first one was that power law. So you
yes, power
term
law.
that law as scale free. I mean, yeah, why are you calling it scale free? I just want to know that.
Scale free, because if you see the word is I'm not calling it, it's a physicist call it, because what happens is if you have a scale parameter, say if you scale the degrees by c, you know exactly a c power alpha will come out from the factor when you are looking at. So in the sense that so you can scale your network exactly.
Can you,
So
I
that's
mean,
why
just explain it with some example? I mean,
no
I
no
mean,
so
I just want to know that. I mean, why we are, I mean, calling it scale free or something like that.
no, scale free means just that you know exactly how to scale the network.
Okay. So I mean that law is known. I mean that
Yes,
power
that law
law.
is known. That law is known essentially.
Okay. And one more thing, that you talked about three graphs. I mean, sparse graph, intermediate graphs, and dense graphs. And you
Yes,
showed it in a pie chart. So, and
yes.
I saw that the areas are not uniform there. Some are
No,
narrow,
no,
and so is that any reason behind that?
no. The reason is that so people have tried to study lots of random graphs. So they have made a plot that how many are sparse, how many are intermediate, how many are dense. So
Okay.
so it's a giving a rough approximation of uh, how many are sparse random graphs. So sparse is quite large.
Okay, I understand. Okay. Now I understand. Okay. Those were my questions.
Thank you.
any other questions? So if not, then let's thanks to Rajat once again for his wonderful lecture.
Thank you, Abhishekda. Thank you for the opportunity, and thanks to the students also for listening to this.
Yes, some real life applications with graph theory. They really enjoyed it. I hope so. And in near future also, we shall again invite you, maybe in a
Thank you.
physical mode if possible.
Yes. That would be lovely. I don't like that much the online version, but still, it's a small world.
Yeah. So thank you
Okay.
to all
Thank
the
you.
participants as well. And that's the end of the today's virtual workshop. And let me